Okay, I'm ready to go back there, if you guys are. Okay. And is everybody here ready to go? Okay, good. Notice the attendance, for some reason, is dropping off slightly.
For some reason?
Yeah.
We're almost to the third week of the term, that's why.
That's probably part of it. Keep working on your homework. Go ahead and cue things up, folks, while I'm still talking. You got the title. Is the title already been up? Title has? Oh, okay. Didn't realize it. Okay. So I guess we're recording. So make sure you try to stay up on the homework as best you can. Use the Math111 study plan as a resource, and expect to see, when we have graded quizzes and exams, expect to see problems like you've seen in the homework quizzes, in your regular homework, all the rest of the homework you've done, and then what you see me present in class. Also, there's that prerequisite little quiz or homework quiz thing that I had set up there. There's no grade associated with that, but there's like 50 questions there from essentially your beginning algebra level stuff. I would suggest you spend a little time on that, because I would assume any of that material is fair game for me to ask you to spot check your skills, because we need those skills to be able to understand the stuff we're doing here. So let's go over here and look at this board for a second, because I want to point out what we want to cover today. And we've already done a number of these items, but I just want to make sure that we kind of organize it today and kind of summarize it all. So what we're doing is we're going to be covering properties of functions, and we'll talk about these different topics. A function can be even, and I'll just give you a little preview on each of these items. An even function, if you look at the graph, it has y-axis symmetry. In other words, whatever it has on its left, it'll have on its right side of the y-axis. So y-axis symmetry is a nice way for you to have in your head what's going on there. And then I'll offer some explanation on how you do it with algebra. Y-axis symmetry. An odd function, you probably think all functions are odd, but in mathematics, an odd function is a particular type of function that exhibits on the graph origin symmetry. And we talked about a point having origin symmetry earlier, a couple sessions ago. So the actual graph of a function will exhibit odd symmetry, or it'll be an odd function if it exhibits origin symmetry. What would be a region on a function where it's increasing? How would you describe that to somebody, where a function is increasing?
When y increases, x increases?
As x increases, as you're moving across the domain, what's happening to the y? Go ahead.
It's going up, I'd say.
It's going up.
Increasing means it has a positive slope and it's going.
Okay, if you would lay a little stick or something up against a curve, a graph of a function, and you see that it's exhibiting a positive slope at a particular point as you move across a region there, that's growing in value. It's an increasing function. So that's a nice way to think of it. Think of it as having positive slope at different locations as you move across the graph. Okay, positive slope. Decreasing, you would expect to see the function falling, having a negative slope at different points as you moved across an interval on a graph. A negative slope. And you can see why back at the beginning of the course we reviewed the concept of slope and the equations associated with straight lines, because it plays into these things called functions. How would you explain to somebody points that are called maxima? Maxima is just plural for maximum, okay? Maxima.
The point at which it turns from increasing slope to decreasing slope.
A point at which it turns from increasing slope, or positive slope, I guess we should say, to a decreasing slope. Now, what's going to occur right there at a maximum? What kind of slope would you expect to see on it?
Zero.
A zero slope, okay? However, what about a minimum down on the bottom of a graph? Down on the bottom of the graph, you'd also expect to see a zero slope, right? So what you'd expect to see going across the top is you can think of a bowl that would not hold water, right? If it was shaped like that, you put water in it. So you'd be going through a location that was a maximum. And the slopes would turn at a maximum. Wouldn't they turn from what kind of slopes am I showing here with my marker? Positive slopes, transitioning through zero to negative slopes, right? That would exhibit a maximum, okay? So positive slopes transitioning through zero slope going negative would exhibit a maximum, okay? Why don't we just say a top? And then a minima, similarly, down at the bottom. And what would the slopes be doing as you transition through a minimum? Negative to zero through zero and becoming positive out the other side. Or holding water, like a salad bowl, right? Or the bottom of a graph, where it bottoms out. Average rate of change, something I don't think I'd mentioned. I did briefly mention it in a class session that we didn't record the other day. Average rate of change is just your concept of slope between 2 points. That's called the average rate of change. So it's something you've been doing since beginning algebra. It's just the slope between 2 points. Instantaneous rate of change. That's something I maybe mentioned in a session we did not record, but all it is if you have a function and you lay a straight edge up against it at some point, it's the slope right at that point. It's the slope of the tangency. I did talk about it in the context of the difference quotient in a session we didn't record. But don't worry about that too much. That is stuff that would come later after this course. But an instantaneous rate of change is nothing more than the slope right at a particular location on a graph. And I'll try to illustrate that before we're done today. Okay? This would be the slope. We can think of it as a slope at a point on f of x. The slope at a point on f of x. And the other property of functions, I guess we could think of it as a property, is the issue we've talked about earlier, domain and range, which are very important. What's the domain again?
Mixed values.
The family of all the inputs, the family of all the possible inputs. Possible inputs. And the range?
Output.
The family of all the stuff coming out of the function, the results, right? The family of outputs, possible outputs. Okay, so let's go ahead and do some algebra associated with all these different items. And we'll start by talking about even and odd functions. First of all, another preface. We are just about ready to start being able to step through from one type of function to another type of function to another type of function. And we're going to do that as we go through the rest of this course. And there's going to be really interesting applications of each of these different types of functions that we'll learn. Now, what kind of functions did you already know before you even started this class? What's the easiest type of function? Linear functions, right? How many of you are making an hourly wage? Anybody want to share how much they're making? $8.40 an hour. Sounds like minimum wage to me, right? $8.40. You work 1 hour, $8.40. You work 2 hours, another $8.40. Isn't that a linear relationship? Okay, that's a simple example. So you've been doing that. That's a simple practical example. If somebody's making $15 an hour, what's their graph going to look like compared to yours? It's going to be steeper, is it not? It'll be steeper, right? So again, linear function, practical application. You've also studied what other kinds of functions already? Quadratic functions, parabolas. Okay, and we'll be doing that. So what we're going to do is we're going to develop a collection of these different kinds of functions as we go through the rest of the course. But we have to understand these properties first. So let's go ahead and hit these. Let's use a sample function. Let's say I give you f of x equals, why don't we do a quadratic function? Something like 3x squared plus 12. A quadratic function. Okay. If I would draw a sketch of this, I'm going to go ahead and do it. And you'll know how to do this. How many of you know what the sketch of this looks like without touching your calculator? A few of you, from maybe remembering something from back in your intermediate algebra. But you're all going to know within about a week exactly how to sketch this thing as quickly as I can do it. It's going to look something like this. It's going to have a y-intercept at, now we all can do this.
0, 3, 12.
What do? You put an input of 0 in, what do you get?
12.
Put a 0 in here, disappears this quadratic term, and you're left with 12, right? Okay, from there, this particular graph is going to take off up like this and up like that. Now, based on what I said a few minutes ago about an even function, it exhibits y-axis symmetry. Symmetry to either side of the y-axis. Same stuff. And you can see that on this picture clearly that it is an even function then, right? It exhibits y-axis symmetry. Let's see how you check it. What if you did not have the sketch? How would you check to see if this equation, this function you see up here, is even?
You replace x with negative x?
Right. You replace x with negative x. Now watch this, if you didn't know that. If I come over to some location over here, let me call it x, how tall is this function at that spot? How high is it right there? I'm trying to train you just like I would if I was a choral director trying to have you all hit the right note, okay?
12, 1. 12 plus 1.
No, isn't it 3x squared plus 12 tall? Isn't that its height right there at that location? Yeah. Don't you put this number in right there, whatever that number is? Put it in here, and you get this value, which then shows up on the graph as your y value. So it is f of x tall. True? Is that true? Everybody feeling good? Okay. If I was over here at x equals 4, I'd put the 4 in as my input. This would become 16 times 3, 48. Right? 16 times 3 is 48. If I put a 4 in, plus 12, up to 60. That would be 60 tall at that location. But I didn't say 4, did I? I said x is the input. So this thing is f of x tall. If I go symmetrically over to negative x, how tall is it over here? Isn't it f of negative x tall? This is my input. The opposite of my x I originally chose. And so that's my input, so it's f of negative x tall. Okay. If this function and graph are even, if they are even, then shouldn't this height match that height everywhere, no matter what x you picked? Yeah. So here's the algebra that you check to see if you have an even function. F of x, that height has to equal that height for the function to be even. So this is what you do to see if you have an even function. Now, how would you do it with this one? You know what f of x is. That's what you started with. That was 3x squared plus 12. And what you do is you come over now and you actually build this. You do the algebra to build this. So this becomes, you go back to your original function and you replace the input with negative x. So this becomes 3 times negative x being squared plus 12, and you clean it up. When you square a negative, that becomes positive, and so you get 3x squared plus 12, and so you observe that your f of x here is the same as this f of negative x. So therefore, and here's the math symbol for therefore, f of x is even. If you understood that, I could give you a very complicated f of x that you had no idea what the picture was, and you could do this algebra test to see if it's even or not. Everybody understand that? Anybody still confused by it? Make sense? Okay. So this is the algebra test without touching your calculators, without having the pretty picture. Other kinds of problems you might see in your homework are they give you a picture and they ask you if it's even or odd. Okay. Let's take a quick look at odd functions, if you have no questions here. Okay. What did I say earlier in summary about an odd function? Must exhibit origin symmetry. Origin symmetry. So why don't should I explain it by example? Okay, let me explain it by example for an odd function. If I drew a picture of something I know has origin symmetry, it might look something like this. Why don't we keep it real simple? Okay, I'm going to call this thing f of x. If this exhibits origin symmetry, then that means if I pick any old point over here, and I draw a straight line down through the origin and go out the other side, the same distance as it took to come from the point to the origin, and come out the other side, I better hit another point on the graph that mirrors the original point through the origin. Mirrors the original point through the origin. Make sense? And every point has to exhibit that relationship. Every point. Let's say I picked, how about the point right here? Wouldn't this one exhibit the origin symmetry also by coming through the origin and out the other side and hitting another point that's kind of a reflection of it through the origin? Okay. So if you see a picture that exhibits that kind of behavior, it would have origin symmetry. Let me draw another one, more complicated than that would exhibit origin symmetry. What if I did something like this? If my triangles were identical, okay? Right? Does that exhibit origin symmetry? Doesn't this point, wouldn't it exhibit origin symmetry to its mirror point down here, even though my drawing's a little off scale? And wouldn't a point maybe right here exhibit origin symmetry with a point right here? And wouldn't this point over here exhibit origin symmetry with this point over here? Okay? So these are examples of graphs that would exhibit that type of symmetry. Yes?
Does the line have to pass through the origin? Like
Yes.
okay.
Notice that word I kept using, origin symmetry. It has to pass through the origin and out the other side an equidistance to find the other symmetric point. Okay. Now, how many of you are artistic? Raise your hand if you're artistic. A small minority, okay, just like me. Although I've said there's a pretty good portion of art in this course, right? Okay, watch this. You all did this as kids. Didn't you take and fold paper? You drew something and you folded paper and did things, and you could see symmetric patterns in elementary school. How many of you have children? If they're in elementary school, you're doing a lot of pattern recognition kind of stuff. And you continue to do that as you go through public education. And we're doing a lot of it here, except it's now on pencil and paper using symbols. We're looking at patterns. So it's something you've been doing ever since you were a tiny kid. So, watch this. If we took this picture, and what if we reflected it or turned it around the y-axis? Turned it around the y-axis. It would then be sitting up over here, wouldn't it, and dropping off like this, right? Okay, keep that in your head. What if you instead took this picture and turned it upside down? Wouldn't they lay on top of each other? Okay, so if you turn this thing around the y-axis, and then you compared that by turning it upside down, and they lay right on top, the result laid right on top of itself in red, that is a graphical way that you can see the origin symmetry as well. So the reflection around the y-axis would be the same shape as if you reflected the graph or turned the graph over the x-axis. Okay. What happens if I give you an equation, though, and you don't have the picture? How would you be able to demonstrate if it has that kind of symmetry? Yeah. Okay. You're on the right track. Watch. If I'm over here at some general location x, how tall is this thing? Remember, I'm training you, right? How tall is that? That's f of x tall, isn't it? If I go to its symmetric location over on the other side at negative x, how tall is it here? F of negative x, right? And for it to exhibit origin symmetry, what must be true about this height and that height? Yeah, the opposite of one of these, the opposite, in other words, the negative of it. Shouldn't the negative of this value be that value then? Or vice versa? Yeah. So the mathematics that you do is the way you typically write it is you take the opposite of your f of x and you compare that with f of negative x.
So shouldn't that height be negative f of x instead of f of negative x? I don't understand why it's the same on this graph as it was over there on the other one.
Okay, what's going to happen? See, let me go back to my story and see if it registers. If I drew something that exhibits the kind of behavior we're talking about graphically, and what we're trying to do is transition from the graph to understanding algebra. So if I come over to some location that on a function that exhibits this origin symmetry idea, if I come over to some general location, this thing is f of x tall at that location. If I go over to the other side, it's going to be f of negative x tall. Now, that doesn't mean it's up here like it was on our parabola. We have to pass through this origin. And then what we're then talking about is how does this height over here compare to this one for it to exhibit origin symmetry?
The height.
It's just the height.
It's not direction.
It's just the height.
Okay.
So this height, if you took the opposite of this height, that's what we're doing here. If we took the negative of this height, shouldn't that match this value? Okay, that's what we're trying to demonstrate. So this is the criteria, the requirement for a function to exhibit odd character. But I'm not going to be totally picky on that.